In this video, we're going to go over some of the 16-bit subroutines that are included with the editor. Okay, all of these subroutines are located in low RAM and golden RAM. We're just going to go to the first of these subroutines. All of these subroutines have counterparts in 8-bit commands. So rotate left and rotate right operate the same as ROL and ROR, but on 16-bit values. In every single one of these 16-bit subroutines destroys whatever values you had in X, Y, and the accumulator. So if you need to save those values, be sure to push them to the stack or store them somewhere in memory before you call these subroutines. To communicate to these subroutines, you're either using the accumulator to point to a zero-page value where the value being pointed to, or the address being pointed to, is the low byte of a 16-bit value. The next address is the high byte. Or X and Y are each pointing to zero-page locations where a 16-bit value is stored, or A is pointing to a 16-bit value in zero-page, and X and Y are an immediate mode. They're a 16-bit value themselves, with X being the low byte and Y the high byte. So for rotate A left, your accumulator points to a 16-bit value in zero-page. You call this routine. That zero-page location, the 16-bit value, is rotated left. The flags that are affected by these subroutines are exactly the same as the flags affected by their 8-bit counterparts, and in exactly the same way. So the shift left and shift right, if the value stored in the zero-page is for shift left, if the most significant bit is a 1, the carry flag will be set. And for shift right, if the least significant bit is a 1, the carry flag would be set. Similarly, for A-Inc and ADCR, they increment and decrement whatever 16-bit value is pointed to in zero-page. Okay, so let's go down here. This group of 6 requires A, X, and Y. So for SB, these are analogous to the SBC command in 6502. SBXY, X and Y each point to a zero-page location that has a 16-bit value. For the ones that end in A number, or A octothorpe, or A hash, or whatever you want to call it, these ones, the accumulator points to a 16-bit value in zero-page, and X and Y are a 16-bit value. X is the low byte, Y is the high byte. So for SB, just like SBC, you have to set the carry flag to get a correct value. For AD, this is the same as ADC, so you have to clear the carry flag to get the correct value. There are reasons for not setting the carry flag or not clearing the carry flag, but you generally have to do that in order to get the correct value. ADXY, X and Y each point to a zero-page location, and ADA number, A points to a zero-page location, X and Y point to the or don't point to anything. They are a 16-bit value. So for the subtraction, in this case, whatever value is pointed to by Y is subtracted from whatever value is pointed to by X. In this case, the value stored in XY is subtracted from the value pointed to by A. In this case, the value in Y, pointed to by Y, is added to the value pointed to by X. The value stored in XY is added to the value pointed to by the accumulator, and so on. And if we just scroll down a little bit more, okay, now CM operates exactly the same way as CMP. it basically just calls the subtraction, sets the carry flag, calls the subtraction routine the appropriate one, and then eliminates the overflow flag, just like the CMP works in 6502. So this next group of six, these are the last six 16-bit functions. And once again, the ones that end in XY take X and Y as pointers to zero-page locations. The ones that end in A octothorpe take the accumulator as a pointer to the zero-page location, and X and Y are 16-bit values. So this is exclusive or, and. And that was really all that was needed for 16-bit functions. I mean, from these you can build up things like multiplication if you want. So let's do some of these functions. Let's write a short subroutine that will test some of these things. So we'll load X and Y with just a 16-bit value, a random 16-bit value. And we'll store these in zero page. Now the editor uses every zero page location from 02 to 7F. So you can use those locations yourself in your own programs, but if you expect to be reading those values back out after you've executed your program and are back in the editor, you're going to have to save them in within your program, have to take them out of zero page and store them somewhere else in memory. So instead of using those, we're going to use some zero-page locations that do not appear to be used by the kernel, and they're in the upper part of zero page. We're going to use 94, 95, 96, and 97. Okay, and now we've got we have a 16-bit value stored in zero page. So we're going to point to that zero page location with the accumulator, and we're going to load another 16-bit value into X and Y. So LDY number, and it doesn't matter. Oops. You can see that you can't do a syntax error in this program. It just won't allow it. So there we go. So now we've got the accumulator pointing to a zero page value. We've got X and Y holding a 16-bit value. So now we're going to set the carry flag, and we're going to call SBA number. So now the X and Y, after calling this, will hold a 16-bit value that is the result. There's 12 of these 16-bit functions where the result is stored in X and Y. And that's the last 12, the compare, subtract, add, exclusive or, and. Those ones, the results stored in X and Y. For the other 6 that operate on the 16-bit values in zero page themselves, the result is stored in that zero page address. So if we exec grok right now, the result of subtracting 4C7F from 6E3C is 21BD. And the carry flag is still set because we did not cross that 0 threshold. So let's say we want to subtract a bigger number. Let's, instead of 4C, we'll go 7C. And now if we exec grok, you can see the carry bit has been cleared, and now the result is negative, so the end bit is set. Let's try a different function. Let's go ADA number. So these are adding 7C7F to 6E3C. And you can see the result is negative, that the overflow flag is set because 2 values that were less than 8000 added up to a number that was greater than 8000. So these operate all pretty intuitively once you get used to them. You run into a problem if you choose ADA number instead of ADXY if that's what you actually meant to do. Let's do a different one here. Let's okay, now this one's just taking the value that's pointed to by A, that 94. So it's taking the 0 page 9495 value and shifting it to the right. So the result will be stored in 9495. Let's just load X with 94, Y 0. And so right here, there's 5 bytes we don't need. Okay, so now if we exec grok, okay, the value when we shift to the right, 6E, 3C, shifted to the right is 371E. Let's change this here to an odd number. Now you can see it's still 371E, but the carry flag is set because that least significant bit got shifted into the carry flag. What's another one that I should show you? Let's try A Inc. Okay, so 6E3D, you increment it, 6E3E. So that's just basically how all the 16-bit functions work. They're very detailed, uh, instructions, I guess you could say, or tables for these functions in the edit.html file. So all of their inputs, all of the flags that are affected, all of that sort of stuff is all listed there in the README file. That's basically it for the 16-bit functions.